Hello everyone. In this video, I will talk about the concept of reference system. Or sometimes called the reference frame. They're the same thing. Alright, so now what is exactly the reference system? It seems like a strange concept. However, I would say that it's actually something that you use every day. Let's look at one example and then you will understand the meaning of reference system. So now let's say here is a two-lane street, and there are two cars traveling in the same direction, side by side, and they're traveling at exactly the same speed. Okay, so let me give them some speed. That's car A, car B, and they both traveling this way. So now let's say the speed of car A is, let's say 25 miles per hour, and car B in the same direction is also traveling at 25 miles per hour. Okay, now that's another, so of course inside car A, there's a driver A and driver B. And on the load side, let's say there's a person standing right here at rest. Okay, so let's call this person C. Okay, now from this person C's point of view, both car A and car B are moving to your right with this same velocity, 25 miles per hour. So when we say that, we're using this person C as the reference system, meaning the velocity that we talked about earlier, 25 miles per hour for both cars, they're actually relative to the reference system C. Okay, so all the velocity that we talk about in everyday language, they're actually relative velocities. And when we talk about that, we actually use a reference system. Use a reference system in the definition of these speeds. So it's already inside the everyday language. You simply just do not talk about the reference system, but it's there. Okay, so we say in this case here, these two velocity is the relative to C. Okay, so so it means that we use reference system C. So what do I mean by use a reference system? When I say that, I mean we build a coordinate system. Let's say that's X and Y and Z, three-dimensional system. The origin is right at the person C. Okay, so as OC here. So it implies a reference, a coordinate system fixed at C. So the velocity is measured with respect to this origin, OC. Okay, now let's change the reference. Now let's say the person B, the car B's velocity relative to car A, meaning that we use reference system A, okay? With A as reference system, then the velocity of B will be 0 miles per hour. So B is stationary relative to A, right? Car A. So you can see that from everyday experience. Let's say you look outside and you see car B, then car B is like at rest. It's not moving at all relative to A. Now, to avoid this confusion, let's say I use both VBs here. Let's put some notation here. Now, let's say I want to say the velocity here is with respect to A, or reference system A. Then I will add this forward slash and then add A here. So that will mean B relative to A, okay? Or you can say use A as the reference system. Now, previously, when I say the velocity of B and A, their reference system is C, so relative to C, okay? And just one more thing here, I want to clarify. So let's say C here is stationary with respect to the Earth, right? So we can also say in this case here, C is equal to the Earth reference system, because it's not moving on the Earth's surface. So that's why C is equal to the reference system we build on the Earth's surface. So in this case, we can say VAC is simply VA with respect to E. E represents Earth. And VBC is relative to the Earth. B relative to the Earth. Okay? And we're going to use this Earth in a lot of cases when we start the reference system. So that's why I want to single out this one to explain that. All right, so that's the concept of reference system. So every measurement or every statement about a velocity is always a relative quantity, relative to something. Okay, we need to specify that. Okay, so I already mentioned the coordinate system built on an object and is fixed with respect to that object. Then we call it the reference system that we do the measurement with respect to. Okay, so that means that sometimes we can. It seems like arbitrary. So that means that sometimes when we measure, let's say the same motion. Let's look at one example. Here is an object. Let's say it's moving with some velocity in some direction. Okay, now I need to specify the velocity here is measured with respect to what reference system. So let me build a reference system here. So with respect to this X, Y, Z coordinate system, and of course it's fixed on something. One example would be fixed on the Earth's surface. Then this velocity is measured with respect to the Earth's surface. Okay? But I can also do the same measurement with respect to another coordinate system, Z prime, X prime, Y prime. Okay, and that's this O prime. So we do the same measurement of the same object's motion inside two coordinate systems. Okay, and let me give you one example. It's the same as the one that we look at here. Now we have a OC coordinate system built on the person here on the low side, but I can also build a coordinate system on driver A. Y prime, X prime, and z prime, and then there's an O prime here. That's using A as the reference system. And we're measuring the velocity of B inside these two reference systems. So that's exactly what I'm doing here. It's just that I generalize to any kind of object you can use as the reference system, and any kind of object that you are trying to measure its velocity. Okay. Now, to be consistent with the previous picture, let me change the notation here. Let's say this one is the O coordinate system. But actually they're the same. Just that I want to be consistent so that you can put this on a previous picture. Okay. Now, when I talk about this velocity, I can have a velocity measured with respect to the O prime coordinate system, right? And then I can measure a velocity with respect to the O coordinate system. Okay, so now the question is, what is the relation between these two? Are there any relation that we can figure out so that when I know the velocity inside one coordinate system, I can easily measure or calculate the velocity of the object inside another reference system? Okay. Now, to talk about that, let's start with the coordinate system. Okay. So when I talk about, let's say, this object, its position vector, let's say it's r. Yep. To make the picture clearer, let me change the position of this object. Let's say it's here. Okay, the object's here. Then I can draw this vector easily. Then I have a position r measured with respect to the reference O, coordinate system O, and then I have a r prime measured inside this O prime reference system. Okay, so we can say now we have position r prime and r. So now if I can figure out the relation between these two, then after I take a derivative of these two position vectors, then I get the relation between the two velocity. Okay, and let's call this object, let's say object A. Then I know this one represents RA prime, and also this one is VA with respect to O prime. Reference system, and then the previous one is the other velocity is A with respect to O. Okay, now this one is A with respect to O prime. That's O with respect to O. Okay, so what are their relations? So let me draw one more line here. Let's see, I can draw this vector. Okay, so now this vector is O prime relative to O. So let me call this R O prime to O. So when we measure the position of O prime in a coordinate system O, then we have that vector. Okay, and let me also make this clear. That's A relative to O prime. That's A relative to O. Okay, so now what's the relation between the two, between these three? So they form this triangle that satisfies the vector subtraction rule that we talk about in the vectors chapter. So now if I look at A relative to O, subtracting O prime to O, if I do this vector subtract that vector, okay, then resulting vector is by drawing the second vectors from drawing a vector from the second vector's head to the first vector's head, second vector's head to the first vector's head, and that is A relative to O prime. Okay, and that means that I already find this relation, right? This relation is here. So now if I take a derivative, then I get the velocity measured inside the O prime reference system from the left side, the derivative, and that equals the velocity relative to the O coordinate system subtracting O prime's velocity relative to O. Okay, so let me call that, let's find a symbol here so that we're consistent. Let's say this velocity is V. Okay, so we actually represent O prime relative to O. So that's the relation we're looking for. We also have some other relations that we can actually talk about. So for example, this this coordinate system relation, the vector relation for the position vector, can also be related to the velocity here. Okay, so now let's say when they coincide, let's say O and O prime, they coincide, that instant is called t equals 0 second. Let's introduce also the time. And so that's the when O prime coincides with O. Okay, and then afterwards the O prime is moving away with this velocity, with respect to O. Okay, so we can write down the R prime, R O prime over with respect to O at any instant is this velocity times t. Okay, so that's what I want to do here. I want to replace this velocity, this position vector using the O prime velocity relative to O times t. Okay, and if you write down the each component for this vector, then for example, let's write down the x component. So x prime, that's inside the O prime system, equals the x inside the O coordinate system minus now is the x component times t. Okay, and then this velocity here is the this relative velocity O prime to O's x component, and I just simplify the notation there. And the y direction, and sometimes we just simply just write down y prime to represent the position measured inside the O prime system. So that's y minus vy and then t. And then z direction, we have these similarly vz times t. And we also have the, I see implying here, so t prime equals t. Okay, so the time in the measured in the two coordinate system are always the same. And this kind of transformation is called a Galilean transformation of two coordinate system. Okay, and after Einstein discovered special relativity, then people know this is not true, right? So it depends on the speed. If the speed is very high, close to the speed of light, then the transformation breaks down. Okay, so we're talking about this for low speed. All right, so that's the relation between the coordinate system or the velocity measured inside two coordinate systems. All right, so in a lot of situations, we want to calculate the relative velocity with respect to some object, right? So that's about the that's about the relative velocity relation. And it actually comes from the previous discussion of the relative velocity. So now let's say I want to call this O prime here, I want to call it C, okay? And A is still A. And I want to call O here B, object B. Then I have the formula I want. So I want to calculate the velocity A with respect to C, then it equals A with respect to B minus C with respect to B. Okay, I have that equation, just a direct transformation, translation from the previous relation. I will have that. And let me also make one more thing clear. So if you change the indice order, let's say C relative to B, I want to change it to B relative to C, then I need to add a negative sign. So if you change the order, the relative object, talking about the velocity of two different objects, right? So this case here, you measure C's velocity relative to B, but now in this on the right side, we're measuring B's velocity relative to C, okay? And they gain a negative sign. Okay, so that's also understandable, right? So then let's say there's a car, let's say moving with velocity v with respect to, let's say, a tree here. Then we say this velocity is to the right, moving to the right. But if you measure the tree's velocity, let's say the driver here, looking back at the tree, then the driver here will think that the tree is moving backward, moving in the other direction. So if I call this C relative to B, then that velocity will be B relative to C. Tree here is B, the car here is C. And that velocity is negative in the opposite direction. That's why we get a negative sign here, okay? And if I do that, then I can change this equation to the one I need, B to C, and then there's a positive sign. Okay, so let's talk about relative velocity relation. So A to C equals A to B plus B to C. And this equation is quite useful, especially when the question asks you to change the reference system, the object that you imagine the velocity relative to, then you want to apply this equation. All right, let's also put some thought into this equation. And if you look carefully, this B here is like a middle object. And object B connects the object A to C. Okay. And let's look at one example. Let's say there's a car A moving with velocity A, and on this two-way street there's a car B moving with velocity B, and we want to calculate A's velocity relative to B. What is this velocity? So you may say, now where is the third object? Where is the middle object that I talked about earlier? So implied in the velocity statement, when we say car A's velocity is VA, we're actually using the Earth as the reference system. So this velocity is relative to the Earth. And similarly, when we talk about B's velocity, it is relative to the Earth. Therefore, when we talk about AB, we actually have this middle object, which is the Earth. Okay, so that's why I can apply this formula. VAB now equals VAE plus VEB. So that's the formula I need. And so now exactly how can I put in some number to calculate that? So let's assign some numbers to these two velocities. So now let's say car A is driving with velocity, let's say 30 miles per hour. And car B here is driving at, let's say, 50 miles per hour. Then we can plug in this equation, okay? So let's see. VAE now is 30. And also by doing that, I actually build a one-dimensional system, x-axis pointing to the right. And that's why this velocity here is positive, because it's moving in the positive x direction. And B here is also positive. So I can plug in a positive 30 miles per hour. Okay. Now how about VEB? What we know here is VBE. And as I discussed earlier, so VEB is equal to negative VBE. And that's why in the coordinate system that we built here is going to be negative 50 miles per hour. So let's plug in a negative 50 here. And the summation gives us negative 20 miles per hour. Okay. Now what's the meaning of this negative sign? So that's the same as before when we talk about kinematics in 1D or in 2D. The negative sign only means that it's in the velocity here is in the negative x-axis. Okay, so the relative velocity of A to B is moving to the left. Okay, and the reason for that is also clear because B is moving at higher speed in that direction. So relative to B, A is moving backward. Okay, A is moving backward. So that's why there's a negative sign here. All right, so can I do a similar calculation? Let's say I want to do what's VBA. Okay, and similarly we have VB here relative to the Earth, and then plus Earth relative to A. And again, I want to add a negative sign here, and then change the intensity to AE, A relative to E. And now let's plug in the number. B relative to the Earth is 50, positive 50. A relative to the Earth is positive 30. So you get positive 20 miles per hour. Okay, so B relative to A is moving forward, moving in the positive x-axis. So that's why. We can also apply this relative velocities formula to multiple objects. Let's look at one example here. Let's say there's a bus. Here's a bus, right, moving with velocity, let's say 20 miles per hour. Okay, so let's call this VB for bus. And then there's a person inside the bus try to move forward, and then will exit the bus. And then this person here, let's call this P, passenger. Its velocities V passenger equals let's say 1 miles per hour. And when we talk about that, this velocity is relative to the bus. So let's put in the complete notation. P relative to B is 1 miles per hour, and the bus relative to the Earth is 20. Okay, so P is the passenger, E is the Earth. And when we say these positive numbers, we mean the coordinate system here is to the right, in the same direction as these two velocities. Now let's say there's a car. Call it a C. C for car. It's moving with velocity. Let's call it VC equals 30 miles per hour in the same direction. And again, when we say that, this velocity is relative to the Earth. Okay. And now the thing about how to calculate the passenger's velocity relative to the car. What's this quantity? Now we can apply the formula that we talked about earlier twice. We can apply it twice. So first, I'm going to calculate the passenger relative to the bus, because that's the velocity that we know from the setup. And then the bus, it's a velocity relative to the car, right? If I need that, if I know that, then I can calculate the passenger relative to the car. But the problem is that we don't actually know these VBC. So we need to carry out the relative velocity formula in a second time. And let's introduce the Earth. Okay, so what we do know is the bus velocity relative to the Earth. So let's use that. And when I use that, I use Earth as the middle object. Then I need to figure out the Earth velocity relative to the car. Then I know, finally, the passenger's velocity relative to the car. Okay, so now let's plug in the numbers. Passenger relative to the bus is 1, which is also positive. and bus relative to the Earth is 20, which is also positive. Now Earth relative to the car is the opposite of this vector, so it's negative. Therefore, when I add up all three numbers, I get -9 miles per hour. Okay, so relative to the car C here, the passenger on the bus is moving backward with velocity 9 miles per hour. Okay, so that's how you do multiple objects relative velocity. And we're not limited to one-dimensional system. The examples here you see, and also this example, they're both one-dimensional. Okay, but we can also do higher dimensional. Let's look at one example here. Let's look at a two-dimensional relative velocity. Okay, and let's look at this example. Let's say there's a river and the water in the river is flowing with velocity. So let me call this W here. Let me call water W. Okay, and with velocity, let's say 2 meters per second in this direction. So when I say that, this velocity is measured with respect to the Earth. So E is for Earth. It's this way, right? Now let's say there's a boat. B for boat. This boat want to cross the river in a straight line. So what we need here is the boat, the final velocity of the boat need to be a straight line perpendicular to the banks to cross the river. And when we say that, this velocity is relative to the Earth, right? Because we're using the two banks as the reference system, and then this the direction of the velocity is perpendicular to the two banks, so it's measured with respect to the Earth, right? The two banks are fixed on the Earth's surface, so the reference system here we're talking about is the Earth. So we need this. We need boat, its velocity perpendicular to the two banks of the river. So now the question is, how do we operate this boat? How do we point the direction of the boat, its velocity, with respect to the water? And let me draw the vector here. So that's the boat direction. We need to point the head of the boat in this direction with respect to the water, so that the boat can end up in this direction, VBE direction. So how to do that? Let's write down the equation that we need here. So when we talk about this boat direction or boat velocity, it's with respect to the water, right? This velocity is with respect to the water. And when we sum it up with the water's velocity with respect to the Earth, then we get this one, right? So what we want to have is VBE equals B relative to the water plus water relative to the Earth. So we need this equation, this relative velocity equation. And now instead of calculating the boat velocity relative to the Earth, I need to calculate boat velocity relative to the water, its direction. How can I determine this one? Okay. All right. So now let's give them some numbers. Let's say the boat velocity with respect to the water. Let's say 5 meters per second. Suppose it's that. Okay. So now let's draw a picture. What we do know for sure is the final velocity will be plus the water's velocity with respect to the Earth. These two velocities are known. We know their directions. So we can draw these two first. And I want to use the red color for this boat velocity relative to the Earth. So what we need to have is finally a velocity pointing this way. Okay, and the water with respect to the Earth is this way, right? So, and remember when I do the head to tail method, let's say vector A plus vector B equals vector C. We use head to tail method, and the second vector which is B here, its head is together with the vector C, the resultant vector's head. Okay, so that's why when I draw the second vector, which is here, which is V water relative to the Earth, I need to draw its head together with the final velocity's head. So that's why I need to draw like this, and its direction is fixed in this right side, right? Pointing to the right, this direction. So that's why I can draw it for sure, this vector. And the first vector is obtained by connecting the resulting vector's tail to the second vector's tail. So that's why I need to connect these 2 points. And that must be the boat velocity relative to the water direction. Its direction must be this direction. Okay, so let's call this direction angle theta. And we know its magnitude is 5. The magnitude of the water's speed is 2. So we can calculate, this one is 90-degree angle. So we can calculate easily the VBE magnitude. So VBE magnitude equals boat relative to the water magnitude squared minus water relative to the Earth squared. So that equals 5 squared minus 2 squared equals square root 21 meters per second. So we figure out the magnitude of VBE, and we know its direction already, right? But the direction here for the boat, that need to be calculated, right? Because we need this angle here to determine how we point the head of the boat. And that angle, let's call it tangent theta, equals water speed with respect to the Earth divided by boat relative to the Earth. So that equals 2 over square root 21. And then you should be able to calculate the angle from this equation. Okay, so that's the two-dimensional relative velocity example. And as a last topic, I want to talk about 2 kinds of reference system. And we call one kind called inertial reference system, and the second one is non-inertial reference system. So what's the difference between these two? If the reference system has acceleration, let me draw a picture. X, Y, Z, S, O, and then okay. So now let's say we have two reference systems. This O-plane reference system has an acceleration A. Non-zero acceleration A. Then we call this non-inertial. And this one has no acceleration. Right? Reference O has no acceleration, so let's call it inertial reference system. Okay, so let's look at one example so that we know exactly what this means. So now let's say there's a truck. Now, if the truck, if we use the truck as a reference system, meaning we build a coordinate system O-plane together with this truck, inside this truck, fixed on the truck, then these coordinates is traveling together with the truck. If the truck here is doing acceleration, with respect to the ground or the earth, then we say truck is non-inertial reference system. Now we can also build a coordinate system fixed on the Earth's surface, and clearly it's not accelerating, right? So the Earth here is inertial reference system. So that's the difference between these two coordinate systems. But of course, if the truck is not accelerating, if the truck is moving with a constant velocity, or if the truck is at rest, then the truck's reference system is also an inertial reference system. Okay. Now the last concept I want to talk about is the breakdown of Newton's second law in non-inertial reference system. So let's call this breakdown of Newton's second law in non-inertial reference system. And to show you that, I want to use this picture. Again, a truck doing acceleration. I want to use it to do the discussion. So this truck with respect to the Earth is accelerating with A. And this A here is the truck with respect to the Earth. And to talk about this, I want to build a measurement system. Let's say there's a table inside the truck, fixed with the truck. And the table here is smooth. And there's an object on a smooth table. Okay. Let's say it's a box. Okay. And the box is sitting at rest right now. Now, once the bus starts accelerating to the right side, because there's no friction, the table here is smooth, so the box will fall behind. So the table relative to the box is moving to the right side, and box relative to the table is moving to the left side, accelerating to the left side. And let's draw a free body diagram for the box. We'll talk about free body diagram in the next chapter, so don't worry if you're not familiar with that concept. but you can look back in the future after you study the free body diagram. So free body diagram means that we need to draw all the forces on the box. Now the box experience normal force, gravity, and in the horizontal direction there's nothing, right? Because the table here is smooth, so there's no friction acting on the box. Now according to Newton's second law, in the horizontal direction, since box experience no net force, net force is 0 in the horizontal. In the horizontal direction. That would mean the acceleration of the box should be 0. B here is for box. The acceleration should be 0. But we see that if we measure the box dynamics inside the truck coordinate system, so let's say a coordinate system built on the table or on the bus. Then the box acceleration in this O-plane reference system with respect to O-plane is accelerating to the left side, meaning it's negative A that we talked about earlier, and this A is truck's acceleration, right, with respect to the Earth. So it's negative this quantity, and then this quantity is non-zero. However, we don't actually have a force in this horizontal direction. So that means that Newton's second law, this contradicts the Newton's second law. So Newton's second law breaks that. Right, contradicts this free body diagram that we drew here. But if I look at the box motion from a person sitting, let's say standing by the truck, standing on the ground, so O reference system is fixed on the Earth surface. So that means that it's inertial. Then we know from this O system's point of view, the box is stationary. The box is at rest, and the truck is moving, is accelerating to the right. So in this case here, the box acceleration with respect to the Earth is indeed 0. So when we say Newton's second law here, the net force equals 0, this A should be measured with respect to the Earth, and that's the 0 that we get here. Okay. But if we measure the acceleration of the box with respect to the O prime, which is a non-inertial reference system, then we don't have Newton's second law. Newton's second law breaks that. Okay, so Newton's second law is valid only in inertial reference system. All right, so now sometimes we want to make Newton's second law also work inside the non-inertial reference system. So how to collect the phenomena that we see inside the non-inertial reference system? The key thing is that you want to add something called a fictitious force, which is non-real. It's not a real force, but it's a force that we add to make Newton's second law work in the non-inertial reference system. So it's an imaginary force added to the non-inertial reference system to make Newton's second law valid. And let's look at one example here. Let's say we're still looking at, before I talk about this, how do I add that? So this fictitious force is equal to negative the mass of the box times the acceleration of the truck in the previous example. So let's say if I add this term, to the free body diagram, when I draw the free body diagram for the box inside the non-inertial reference system, then I add such a force. Now remember, it's negative ma, and a is to the right, so negative ma is to the left. So if I add this force, then Newton's second law is true, right? Because this equals exactly the box acceleration relative to the truck. So inside the truck, when we look at the box is accelerating to the left. Okay, so that's exactly what we need. So now let's look at an actual application of this. So now let's say there's on a playground, there's a big rotating disc. It's rotating with some angular velocity omega, and let's say there's a person sitting here, okay, sitting at rest with respect to the disk, and it's doing rotation. Now, if we look at this person, its free body diagram, then we know there's a normal force, there's a gravity, okay. Now, in the horizontal direction, we should have nothing, okay, But if you ask this person how this person feels when this person is sitting on the disk, then this person would say the person feels like being pushed by a force pointing away from the center. Feel such a force here. And this force is the fictitious force. And its magnitude equals, let's say the mass of the person is m, equals negative m. Suppose the radius here is r, negative r omega squared. Okay, and r omega squared is the radial acceleration of the disk at the rim, right at this radius r, and the disk has this acceleration. Right, but we already talked about that. We need to add a negative sign when we talk about this fictitious force that the box feels. And in this case here, we add the fictitious force opposite to AR, because AR is pointing toward the center. Okay, so this AR here, okay, is pointing toward the center. That's the centripetal acceleration that we talk about in a circular motion. But now when we add the negative sign, then it changes the direction to outside. So that's why this person feels like being thrown away or being pushed by a force pointing outward, radially outward. Okay, so that's one application of the non-inertial reference system that we talk about today. Okay, because clearly this rotating disk is a non-inertial reference system. of the system. Okay, so that's all for today. Thanks for watching.